All right, number 5. Let's see. 5 was, well, shit. Come on. All right, why am I looking at this? All right, hold on, everybody. Bob, 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 Bob. There we go. Okay. Okay, here we go. Okay. So 5. Oh, rewriting in standard form. Okay. All right. So everybody had this problem. So number 5 is said rewrite in standard form. Standard form, of course, is this one. So you can see the vertex. And I said use completing the square, specifically said that. So if you use the shortcut, no, too bad. So everybody had this problem and nobody had this problem. Oh, let's see what would be good here. Yeah, plus 39, sure, okay. So how do I get this started? What do I need to like move out the way, and what do I?
Don't you take out 4, and so then it's x squared plus 6x.
Move the 39 out the way. Now you can figure out what goes there, right? Right, what would it be?
It's 9.
Yeah, half of 6 is 3, squared is 9. So if I add 9, I actually just added
36.
36, so I better subtract 36. Does everybody understand that part? So I got to do the Indiana Jones thing, right? Take the golden statue, put the sand on there. I got to balance things out. So if I add a bag of sand, I better subtract an equal weight. Right, so this is not really 9. Same way this is not really 6. This is not really 6, it's 24. I've just split it. So this is not really 9, it's 36. So I better subtract 36. So now I've got this. So what's the vertex?
-3 plus 3.
Yeah, I like it. So you do the same thing on number 5. Is that right?
Yes, thank you.
Sure. That's what I'm here for. So let me address something. I already had a discussion with one student, and there was only one student that I pretty much decided it was a clear-cut case of cheating. But there were a couple other students who the answers were in the same format that this application called Photomath would give. So if I don't have really hard evidence that that's what happened, I at least call it out, and then I hope that somebody's going to talk to me about it. Do not take it personally if you did not cheat. I hope you can understand that I'm not here to make your life shit. I am here to, if I think somebody's cheating, I want to protect the integrity of the course, and I want to not degrade the work that other students are doing. Does that make sense? If you think you're going to pass cheating and some other student is going to barely pass or maybe even fail when they are putting all their soul into their work, I'm not going to sit by and let that shit happen. Now, at the same time, I make mistakes. Everybody makes mistakes. So unless I really, really have good evidence that I was cheating, I'm not going to give you a 0 for something, right? But I'm going to call you out, and you got to be careful. So if you really aren't doing that, continue not doing that. I love it. If you are, you better stop, because I'm going to keep an eye. And I know some other places too, not just Photomath. There's some other places to get some information. Just know that I know they exist. And it's all bullshit. All of it is bullshit. That is the worst thing to me, to do that stuff. And again, if you're not doing it and I call you out, I apologize right now. I don't want to do that to a hardworking student. That's the last thing I want to do. But I need you to work with me and understand why I might do that. Okay. Is everybody with me on that? So just, a lot of these things are awesome study guides. They're awesome things to use to help you learn stuff. Unfortunately, some people don't use them that way. So, okay. Anything else from the quiz or from homework or anything? Everybody else good? Everybody good? Okay. All right. Let's see. So we left off in.
Were we gonna go over the slant asymptote thing?
Yeah.
Okay.
Let's do that. Let me see. What was the problem I was going to do? Here it is. Wait. So I want to do an example from 5-6. Let's see. I had it here, and of course I moved around. Here we go. Perfect. So like, let's do this one. Let me write this up on the board. Yeah, sure. Volare. Okay, let's do this. 2x squared plus x minus 1 over x minus 4. Where'd you guys go? There you are. All right. So help me out. Let's do every piece of this. I'm so far away. How do I find the X-intercept and the Y-intercept?
The x-intercept, you would make the top equal to 0.
Cool. So I got to do 2x squared plus x minus 1 equals 0. Whenever I have numbers here that have only one way to factor them, that's when I'll do this, and I'll just figure out, I know those are ones, and then I'll just figure out, okay, that's got to be a plus and that's got to be a minus. So I get 2x minus x is positive x. Is that cool? I mean, it's relatively simple. When you have numbers that have only one way to factor them, then there's only one way. It's just up to the signs. Okay. So then I can see my x-intercepts, my roots.
1/2 and -1.
Yeah. And they're both multiplicity 1. So what's the graph going to do at these? Go through. I like it. And there was, real quick, I'm not calling anybody out. I can't remember who it was, but somebody was writing the word through and they were writing the word turn. So they actually looked the same. I don't know. I couldn't tell. Anyway, sorry. I like that little side note. So if it was you, I'm not saying who you are. I forget who you are anyway, but somebody, I couldn't tell if it was the word through or the word turn. So just be a little more careful when you write. You didn't have to call yourself out. I didn't even remember who it was. I just thought it was kind of funny. What about the Y-intercept? That was easy, right?
Equal to 0.
Yeah, 0.
1/4.
1/4. I mean, you gotta love that shit, right? Y-intercept easy. All right, I'm not so interested in that. What about vertical asymptote?
4.
Yeah, x equals 4. Remember, vertical asymptote is a line. There's the equation of the line. What about horizontal? Is there a horizontal asymptote?
No.
No, because the top degree is higher than the bottom, it's actually a slant, which is the whole point, right? So how do I discover the slant? It's exactly the same as this, doing 8 into 11 and getting 1 and 3/8 and then taking the whole part. That's basically the idea of the slant asymptote. So when I divide this, I'm going to take the whole part of the answer, because again, can somebody please tell me, where do horizontal asymptotes come from?
Getting as close to it as possible.
No, that's vertical asymptote. And that's sort of like the behavior at the vertical asymptote. Where do horizontal asymptotes come from? Letting X. Sorry?
The biggest terms of the denominator and the numerator.
Sure, that's how they determine what situation you're in. But where do horizontal asymptotes come from? They're actually the equivalent of end behavior. Letting X get really big, positive and negative. So remember that. Where do vertical asymptotes come from? What's not allowed from the domain. Horizontal asymptotes come from letting X get really big. Same thing with slant, right? So that's going to make this make more sense. Why do we pluck out a piece of this answer and throw the other piece out? What you're going to see in a minute. So I'm going to do this kind of quickly. 2x squared minus 8x, change the signs. 9x minus 1 plus 9x minus 36, change the signs. 35, it doesn't really matter. What's going to happen to this last piece when I make X get really, really, really big? What's 35 divided by 18 trillion? It's basically
0.
0. So that's why this is the slant asymptote, because it is built on letting X get really, really, really big, positive or negative.
How do you divide if it's like x squared or 2x squared minus 4 instead of x minus 4?
Oh. So the worst case, I don't know. Do you guys want to graph this or what? Anybody?
Do you graph the slant asymptote?
No. Yeah, of course you do. So, all right. So really quickly, what do I got? I got 1/2 -1. I got 1/4. I got 4 is my. Let me see if I can kind of do this quickly. X-intercepts are 1/2 and -1. That's looking kind of gross. I do have a Y-intercept, which is kind of nice. Let's see. And so let's go ahead and set up a Y scale. Let's see, probably up to 9. So let's do 2, 4, 6, 8, 10. So there's 9. So then 2x plus 9, yeah, this kind of sucks a little bit. It would go up 2 over 1, and it would go forever from there. It doesn't really matter, Jeff. What would it be? Yeah, maybe that looks about right. -4.5. Well, I'm a little off. Screw it. It's all right. So there's a wall there. There's the slant asymptote, right? Let me make that less of a point. All right, let me stop for a minute. So all I've done is I plotted the intercepts, the X-intercepts, the vertical asymptote, and the slant asymptote, right? So here's what kind of neat about this. Notice on this side, above this, it could either be down here or it has to be in here. How do I know it's in here and not down here? If it's down here, what's got to happen here?
Another X-intercept.
There's got to be another X-intercept. There is no X-intercept, so it cannot possibly be over here. So it must be up here. So if I threw 1, 2, 3, 4, 5 into the function, I would get a value up here, and it would be doing, well, let's make it something legal, Jeff. Legal's always nice, I've heard. All right, there we go. So it's gonna be something weird like this. Way this shit up here. Let's see, what do we get when I put a 5 in here? 55, 54, I get 54. Yeah, so it's gonna be way the hell up here. So see how that's kind of cool? The walls always cut things into regions. If there had been an X-intercept here, I would have known it was down here. And it would kind of go up and it would approach this line. But there is no X-intercept, so it must be in here. And if I throw 5 in, sure enough, it's way up at 54. So it's going to be way up here.
How do you know what the inside graph will look like?
Well, it's sort of restricted because it's got to be curvy, because it's a polynomial. And if I kind of look, here's 10, 20, 30, it's going to be off the freaking chart. But I know that 5 has got to be going to 50 something. I know it's got to go up against this wall, and then it's got to go up against this wall. So it's got to look basically like that.
What about the side towards the origin?
On this side.
Yeah.
So right here, this is
Yeah.
kind of nifty. It's going to go through both of these, right? Let me think. Where am I at? Oh, and the Y-intercept is 0, 1/4. So since it's going to go through both of these, remember, because of the first, the multiplicity, it's going to go through. It's got to look like, I really want you guys to get this. The only way this could look is like this. I drew that horribly, but do you guys get that idea?
So together they made a parabola?
It's not really parabolic, but I can understand why you would call it a parabola, right? I can't let it go now. It's going to suck no matter what you do, Jeff. That's basically exactly the same thing. Okay, good job. Do you see how this goes forever? Are there any X values that are left out? As this goes forever down, right? And then this, the only X value that's left out is 4. Because this will have outputs for every X is going to have an output. This is going to keep going. Every X is going to have an output, correct? I know I keep going off the whiteboard, but.
How would you then, I guess that would be Y equals 2X plus 9. That's how you would write it?
Oh, yeah. So the slant asymptote officially would be Y equals 2X plus 9. So vertical asymptote is X equals. Horizontal asymptote is Y equals, or slant in this case.
I forgot to ask real quick, while we were talking about the local and end behavior, how would you annotate that? Like, how would you write it?
So the book, when they say local here would be 4, the vertical asymptote. So as X goes to 4, the function goes, what does the function do as X goes to 4? What's the function do?
Down.
Goes to
Infinity. Negative infinity.
negative infinity. And as X goes to 4 from, this is from below. As X goes to 4 from above, and you could use words instead of symbols here if you wanted to. What happens as X goes to 4 from above? What's the function do as the inputs go towards 4 from above?
Positive infinity.
So it's basically this idea. It's going to negative infinity from this side and to positive infinity from that side. So you can say from the left, it's going to negative infinity. From the right, it's going to positive infinity at 4, if you wanted just to say it in English.
Okay.
Now, somebody's got a really good question to me in chat. It was a private chat. And it says, why did you not synthetically divide? I could have, totally. Do you guys see that? Totally could have synthetically. I just want you to realize that a lot of the time you can't synthetically divide to find slant asymptotes because this might be a higher degree than 1. But it is a degree of 1. You can synthetically divide, sure. No worries. Okay.
And then could you please go over the worst situation in a long division?
What do you mean?
You were talking about like if there was coefficients and different.
Oh, yeah, that's right. Does somebody
yeah.
else have another question on this here? So I really notice this. I don't think I've made a big enough deal out of this. How many regions do I have to worry about in this graph? There's really there's kind of 4, but there's really 2. It's one side of this and the other side of this. So on this side, it could have been up here or down here. And on this side, it could have been like this or like this. And we obviously discovered where it was. So the vertical asymptotes break it up. So I've got to find out on this side, where is it? And on this side, where is it? Because I have a lot of students that are sort of like, they don't look at it. They think that they have to worry about this side and this. No. This is all the same. If it was up here also, would it be a function? No. So you always break things up according to the vertical. I don't know if that made enough sense. Okay, maybe. Okay.
Sort of like the piecewise functions from earlier.
Yes, exactly. It's a lot like that. Let's see. So I'm going to erase all this, and I'm going to make a gross long division. And then we'll finish up chapter 5. We basically already did finish up chapter 5, to be honest. Yeah, okay. So let's see. Oh, that's gross, Jeff. Can we just not make it that gross? There you go, buddy. Feel better? Yeah. I'm trying to think ahead, but it's not going to be easy. Okay, sure, whatever. So why does this suck? A little bit. Because 3x times what is x squared? I think this is what you're talking about, right?
Yeah, that. And is it possible for the smaller one to have an exponent as well? Like if...
Of course, sure.
Okay.
You mean like this?
Yeah, like if that was, and then I guess the other one would have to be bigger, or it wouldn't matter?
Well, no. In order for this to mean anything, this degree has to be at most equal to this.
Okay.
If not less. Right? Because if it was a cube, then I can't multiply it by anything. I actually have to divide it, and that's the whole, it's already dividing. So there's nowhere to go with it.
Okay.
Yeah. I don't know, did you want to look at this, or are you cool with this? I don't know what's happening. So like here, it'd have to be 1/3. Do you guys see what I'm saying? And then 1/3, it would be x squared minus 2. Then I make that minus plus. Oh, sorry. I lined it up with the wrong thing. There we go. So then this would be dead, and this is 7x plus 3, and I don't care. How do I know I'm done with the dividing? Because this degree
Is smaller.
is smaller. I like it. So then I know I'm done, and I can put plus 7x plus 3 over 3x squared minus 6. Now, why does this make sense? Wouldn't this look like this? Blah, blah, right? This is kind of cool that we did this problem. What situation am I in? The degrees are the same. So how do I figure out the horizontal asymptote? Degrees are the same.
It's the ratio.
The ratio of the highest powers. Isn't that what we got? If I could let this go to 0.
Did the 6 not mean anything when you divide? It only matters when you multiply it back.
What do you mean? Sorry.
The 3x squared minus 6.
What about, yeah, so the minus 6 is why there's a 2 there, right?
Yeah.
Okay. But in one sense,
right, it doesn't influence anything on top though.
It didn't, because its influence was here, and this goes to 0. So I could have put minus 6 billion and 1, and it would have been the exact same answer here, and this would have been different, but who gives a shit, because it goes to 0.
Okay.
Okay. All right, I like it. Okay. So what's interesting is this procedure finds slant asymptotes, but it cannot give a different answer for other things. So if I do this and I get a 1/3 horizontal, this has to also give me 1/3. But why don't I do this? Because why would I have to? Because I already know the shortcut, just take the ratio. I don't need to do all that shit. But this is just a nice example of all the different methods we have to agree with each other. It's just that some are better used in certain situations. Okay. A lot of cool shit just happened. I like it. Anything else before we get back into anything? No? Okay. I don't know if you guys heard when I just said we basically finished 5-7. There's really nothing new in 5-7. 5-7 is a very strange creature to me. But it's there, and it's a nice review of inverses. So in this section, you're going to see some inverse questions like find the inverse. They do have more finding the inverse of radical functions and polynomial. Oops, I almost ended the meeting. That's good, Jeff. So what do I mean by that? I mean finding the inverse for something like this. Right? So what do I have to be careful about when I'm trying to find the inverse of something like this? What's wrong with that? Oh, that was probably a mistake. I don't know if you guys have picked up on this. Now, don't take the wrong message from what I'm about to say. But if you turn something in like within a day of the due date, I'm not going to come down on you too hard. I'm not going to care that much, right? Especially in the environment we're in. The due dates are there to keep you going so you don't get too far behind, right? So if I didn't put any due dates, there'd be some crazy fool or several who would try to do all the homework the night before something. And I'm like, that's not good. All right. So don't worry too much as long as you're continuously working on stuff. So can somebody tell me what is the issue with this?
You would initially switch the Y and the X, right?
Okay, but what's wrong with even starting that off? I mean, they kind of tell us right here, but would this pass the appropriate test? What test would I use to figure out if this is invertible?
It's not a function.
No, it is a function. It passes the vertical line test.
It's not the horizontal one, though.
Horizontal line test, because it's parabolic, right? What's the vertex of that thing? Anybody? Let me put it up here.
-3.
Yeah. So it's x minus 2 squared minus 3. So 2, -3 is the vertex. And of course, this completely does not. Can I figure that out real quick? No, I don't care. I don't care. So it completely does not pass the horizontal line test, right? Well, I could have done that. Let's at least do that, Jeff. Let's make this a little better. What's the Y-intercept? Anybody?
1.
Yeah, if you put a 0 in, you get 4 minus 3 is 1. So let's at least be that good, Jeff. Since that's 1 there, 1, 2, 1, 2, there's got to be a 1 there. Is everybody cool with that? That's the good old symmetry trick, the mirror image point. Okay, so that's a little bit better. Good job, Jeff. So what do we do if I have a function like this and I want to invert it? I have to make a choice. How do I restrict the domain? What's the domain currently is -infinity to infinity. That's the problem. Because part of it kind of.
You have to cut it in half.
Yeah.
At
How?
the vertex?
Sure. How?
Like 0 to infinity?
No.
Oh, no, 2 to infinity.
Yes, there we go. So if I cut this part off, so then it only goes from here. So now I'm going to make my new domain, restricted domain, will be from 2 to infinity. All right, so let's see what that means. So now let's do the process. Oops. So like you said, I would switch the X and Y. Right, this is all old news. I'm going to add 3, take a square root. Is that cool? Can you guys handle a couple things? And then add 2. Can you handle everything at once? Add 3, bam. Take a square root, bam. Add 2, bam. But when I took a square root, it would be plus or minus, right? So how do I tell, based on my restricted domain, how do I tell which one it should be? So watch this. Let me rewrite this a different way. If I want, now remember, all right, stay with me. This is one way to do this. If the domain of my original function is 2 to infinity, what should the range be of my inverse function? Because what did I do very first thing when I was finding my inverse function? What did I do?
Switch the two.
Switch the x and y, which switches the domain
And range.
and range. So my range should be 2 to infinity of my answer. So do I want to do 2 plus positive, or do I want to do 2 minus positive? Considering I want my range to go from 2 up.
Plus.
Plus. I really want that to make sense. I have a plus or minus. If I do this, then 2 is the biggest because I'm subtracting from it forever. So wouldn't it go from 2 down to negative infinity? Oh, shit. Now it goes from 2 up to infinity. So if we would have broken this in half the other way, if I would have gotten rid of this, then this would have been 2 minus. That would have been the actual inverse. That's the key. And they give you a couple examples where they explain how the choice is made when you get to that point, when you take a square root, how do you choose which one? Well, it depends on which way they either told you to do this or which way you chose to do this.
So would our range now be -3? Or our
No.
domain, sorry.
Domain, yeah, domain. Now real quick, what's the domain? What's the range of this? What's the range? We killed this. What's the domain of
-3
our
to
original?
infinity?
Say again, sorry?
-3 to infinity?
Good, -3 to infinity. So what should the domain of my new function should be? Should be this.
Yeah.
Yeah, so every y switches with x and every x switches with y. So the domain, and is the domain -3 to infinity? Yes, just like you were saying. I really want that to make sense. That kicks so much ass. If you go into a problem knowing what the range and domain are, your inverse should turn those, should invert those. That's what an inverse function does. It switches every x with every y. That's such a beautiful little check to make. Did it get the right answer? Well, it does these. Oh, good. Next. All right. That's a great check to make. Okay. Maybe.
How does that translate in rational functions?
Oh, it doesn't. So this is from section 5.7. This is the last section of chapter 5. And it's all about inverses and radical functions. So 5.7 has nothing to do with rational functions. Yeah. Rational functions were all in section 5.6.
Is on a radical function that you have there, the new function that you wrote, do you find the vertex by looking at that the same way? Like is 2, 3 the typical vertex for the typical formula of a radical function?
There's no vertex for, I understand what you mean. It's kind of like, so this poor graph has been through enough. All right, it's poor graph. But I want to bring it back real quick. So if I look at, real quick. So here's what it was. And what did I figure out? I forgot. There was something here. So there was something here, I think it was. Yeah. So there's so when I flip it, it should look, now this goes to -3. So this should be -3, 2, right? It should be here.
Yeah.
Mirror image. And then it should go, then it should go, this is kind of freakadelic. It should go like that, right? They're going to cross each other somewhere over there.
Okay. Does it matter that it sort of stops or has a stopping point there? Like it has the vertex turned into a sort of origin?
No. When we did this is no longer parabolic.
Yeah.
It is this. This part is gone because we did that. So this isn't really a vertex anymore. It sort of is. And this sort of is. It's like a parabola that's missing its other parts. So in that sense, this is kind of like a phantom vertex point. Like, I don't know, it can have phantom pain there. I don't know.
But I mean, like, it's an origin, it's a stopping point,
Yeah, it's sort of like
or rather a starting point.
a ray has a beginning point. Yeah.
Okay.
All right. Interesting questions. I like it. Okay, guys. So it's all about choosing a way to restrict it. You cut it at the vertex. Normally, I would almost always pick the side that's positive. That's this side. That kind of makes everything easier. But they might have a problem where they ask you to cut it the other way. So you just got to be careful when you get down here. Plus or minus, which one do you choose? All right. And of course, the one that we threw away would have been this piece. That would make it a complete sideways parabola, right? So the one that we threw away would have been this piece. But it can't be there because then it wouldn't be a function. Okay. All right. So that section has a lot of stuff that we've done things with before. So I'm hoping it's not going to be too evil. We'll find out. So let's step a little bit into chapter 6. I want to ask you guys, when I say the phrase exponential function, or even if I just say exponential, what do you guys think about?
Goes on forever.
Goes on forever. I like it. I don't know if you're talking about my lecture style or growth. I like it. Oh, this guy goes on forever. It sounds familiar. Okay. Anybody else besides me watch horror movies where there's like a creature and they're like, it's growing. How is it growing normally? It's growing exponentially, right? Or virus spread. Today it's New Jersey and tomorrow it's the world because of exponential growth, right? And of course we lived through that. So those kind of horror movies, we're going to be like, whatever, been through that shit. So this is what we're getting into is these types of functions. And here's what they're really, really based on. Okay. And Manda, you got it perfect. They are based on growth or decay, which is like negative growth. It's like, but what kind of growth? Not linear growth, right? So for example, if I have a function and I know it does this, what, Jeff? I have a function and I know it does this. Is that exponential growth? I mean, it is growth. Do you agree with me? It is growing.
It's not exponential though.
So exactly. Does somebody know what kind of growth this is? I kind of gave it away just a minute ago.
Linear.
It's linear growth because the slope is the same. It always goes up 4 every 1 step, up 4 every 1 step. So this is always adding the same amount. That's linear growth. Exponential growth is when I'm always multiplying the same amount. So what would that look like? Well, one of the most easiest cases would be this here. What do you got, Jeff? I don't know. Sure. So it's obviously not linear. I don't keep adding the same amount. But what do I keep multiplying by?
It's 2.
Yeah, so I keep multiplying by 2. Okay, I like it. So this one, of course, is y equals 4x, correct? 4 times 2, 4 times 3, 4 times 4. What would this equation be?
Due to x power.
Yes. So the reason this is 4x is like up to here, this is 4 times 2, right? And then this will be 4 times 3 when I throw that in. This will be 4 times 4. So it's 4 times x. This would be 2 times 2, which is 2 squared. And then this would be 2 to the 3rd power. And this would be 2 to the 4th power. So in general, it's 2 to the x. So it's just capturing the pattern that we see. So that is constant doubling, right? So that's very, very strong growth. That's crazy growth. If you see the blob monster growing like this, just pack it in. You're doomed, right? Well, unless this is every century, then, we got time. Okay. So let's talk about, let's look at this guy a little bit more closely. Let's fully flesh this guy out. Let's throw in some more numbers, like negative numbers. All right, so let's analyze this dude. So finish this table real quick. And I mean, real quick, I shouldn't have to say this, but you see why we call these exponential, because the variable is in the exponent. It's crazy, right? Us math people, so creative. We call this function, it's exponential. Okay. I'm allowed to make fun of math people because I am one. So what did I get here?
4.
No.
1/4.
Yes. 2. Any negative power means what? Negative powers mean
1 over
Flip.
that thing.
I like it. Negative powers mean flip. If it's up top, it goes down below. If it's down below, it goes up top. It just flips. So what's 2 to the negative 1?
1 over 2.
1 over 2. 2 to the 0?
1.
1, right? Anything to the 0 power is 1. By the way, let me know. You can private chat me if you want to. If I can show you why this is true and negative power means flip, and I can show you why 0 means 1. If anybody asks, I'll show you. If not, I'll assume you remember and you know, and it's all good.
What if it's negative 2 to the 0?
So wait. All right. If it was this, like that,
Yes.
all right. What's that?
1.
So what's that?
1. Same
No.
thing.
No.
Negative 1.
That's 1, and that's got a negative in front of it. So did you mean
Oh,
this?
1 over 1.
Did you mean this?
Oh.
So that is negative 1. Negative 1. What's this? What did I just say? Anything to the 0 power is?
Negative 1.
No.
Or
no.
1 over.
There's
1
no
over.
negative power. No 1 over, right? All right. Maybe we should focus on this. Okay. All right. Real quick. Let me just finish this out. I think, yeah. So 2 squared is 4. Okay. So hold on to that for a second. Okay. What do I get? Real quick. We'll do a couple of these real quick. What is this? What's x cubed divided by x cubed?
1.
1. What's another way to look at this? What do I do when I divide? Don't I subtract powers? Correct? What's 3 minus 3?
0.
0.
All right, so there you go. Anything to the 0 power is 1. Except for 0. 0 to the 0 power is evil. It is an evil. Now, to be honest, I love this. This means it's a neat problem. But just to tell you the way the average person would look at this, it's evil. It's not undefined. It is indeterminate, which is a whole other level. So we're basically not going to worry about that. We're basically assuming that's not 0 because that's the only number that this is not true for, right? What's 0 to any number? 0. What's any number to the 0 power? 1. So what is 0 to the, oh, it's 0. No, to the 0. Oh, it's 1. Oh, it's 0. Oh, it's 1. Oh, it's 0. Oh, it's both. It's both. No, it's neither. Oh, shit. All right. So no, we're not going to I have no idea if you guys went with me on that journey. There's a lot more to that. If you take calculus, you will actually directly analyze that in different situations. Okay. Stay with me. What is this?
Followed by x.
Good. So 3x's cancel. Do you guys see that? 1, 2, 3. And there's an x left on the bottom. Now, what's the other way to do it?
X to the -1.
Yeah, 3 minus 4 is -1. So what's a negative power mean? It means flip. That's it. That's all a negative power means. All right. So if I see anything to the 0 power, that is 1. Anything except 0, just we're assuming it's not 0, right? I could have a whole lot of shit in here divided by Jeff, and then raised to the 0 power, it's 1. If I put a negative in front of it, of course it's -1. Because it's negative this. That's 1. So that is, let me make sure you guys see that, -1. So this is an old thing about like -2 squared versus -2 squared, right? This one does not have the negative squared. So it's 4 with a negative in front of it. So, and the other one, of course, is +4. So this is 1 with a negative in front of it. Whereas this, anything to the 0 power is 1. Okay. Good old order operations come to save our ass. 1 yes. Okay. A 1 yes. Okay. So, looking at this, what will happen? What's isn't this getting? What's going to happen if I keep going this way? -3, -4, -5, -6. What's going to happen?
Closer and closer to 0.
Does it ever get to 0?
No.
I love it because 2 to the negative number would be 1 over 2 to a number. The only time this could be 0 is if the top is 0. When is 1 equal to 0? Never. So that means that this thing is going to have an asymptote at 0 going backwards. So this is the first time we're seeing an asymptote that only works in one direction. Because what's going to happen if I keep going this way? Right? If I just keep going this way, what's going to happen?
Infinity.
Infinity. I love it. So if we graph a few of these things. So -1 is 1/2. 0 is 1. 1 is 2. 2 is 4. 3 is 8. So it's going to go like this. That is an exponential. Would the shape fundamentally change if that had been a 3? No. It would have been steeper here and go down faster here, but the shape would have been the same. Does that make any sense? So this is basically the shape for anything like this where A is greater than 1. What happens at 1? What if A was 1? If the base is 1, why is that kind of silly?
It's a line.
Yeah, it would be a straight line at 1. 1 to any power is 1. I like it. What's 1's the ith power? Just be quiet.
What happens if A is less than 1?
Bringing no Jesus. I don't know what Jesus is. Sorry, say it again. I was stuck on your.
If A is less than 1.
Oh, okay. Real quick word about. Okay. I should have said not A greater than 1, but it's a little weird because it would work between 0 and 1 also. But what really gets weird is when it's less than 0. 0 obviously is a bad choice, right? So here, let's look at this. Let's do something right now about between 0 and 1. So you understand why 1 is no good. 1 would not have the shape because 1 to any power is 1. It would just be a flat line at 1. We go, oh no, our function is dead. Okay. Okay. Between 0 and 1 is interesting. I'm going to take this away. Has everybody got what they want here? I'm going to assume yes. So what if I had y equals 1/3 to the x? So look what happens now when I put -2, -1, 0, 1, 2. That's my standard 5 go-to points when I don't really know what something looks like. So help me out. What is 1/3 to the -2 power? Negative tells me to
9.
to 9. To flip it, and then square means 9. I love it. So, and then 1/3 to the -1. That's right, kids. And then 1/3 to the 0 is 1. 1/3 to the first power is 1/3. 1/3 squared is 1/9. Do you see how it's doing everything the other one did in reverse? It's growing this way and shrinking that way. That should kind of make sense. So it looks like this. Now even my blue pen is dying. Damn it, you were my last hope. Blue. Sorry, that's Jurassic World. I don't talk about it. All right, so -2 is 9. Shit. Might as well. Why not? -2 is 9. -1 is 3. 0 is 1. 1 is 1/3. 2 is 1/9. So see how now it's going to an asymptote this way and is growing the other way. Do you see how, if it was 3 to the x, wouldn't it have been this? Right? Well, if you could just do it better, Jeff. There we go. Okay. Isn't that the reflection? Isn't that a reflection around the y-axis? Isn't this, by the way, isn't this?
It's just the inverse.
Isn't this? Do you guys agree with me? What is 1/3? Isn't it 3 to the -1? And what do you do with the powers? Don't you multiply them? Isn't this a reflection around the y-axis? Which is exactly what it did. So when the base is between 0 and 1, it becomes decay. This is like the decay of radioactive material, right? I like it. Hey, Mikey. All right, let me think. I'm just gonna do something else next. Shit. Oh, that's right. So here's the freaky thing. What about a function where the base is less than 0? What would be the problem with that? So of course we're talking about negative base now, right? Would a negative base have a problem with any powers? So if
Only
A
odd?
was, well, no, what's -1? If I have the function -1/2 to the x, it can handle first power, third power, right? Third power would be -1/8. Who cares? I don't know why I had to make it 1. Let's just make it, all right, look, sorry. Let's make it -2 to the x, right? 2 would be 4, 3 would be -8, no worries. What about 1/2? What if I put 1/2 in for x? What would that mean?
1/4?
No, come on. What does a 1/2 power mean? What's a 1/2 power mean?
Oh, a radical?
Yes. And then we're getting into what territory?
Imaginary numbers.
But, yes, you're right. But what about what's 1/3? That wouldn't be imaginary, right? I could take a cube root of a negative number. What about 1/4? Oh shit, what about 1/5? Fine. What about 1/6? Oh shit, what about 1/7? Fine. So this is constantly existing and then not existing, and then existing and then not existing. So that's why we basically don't let the base be below 0. Do you understand? That was this actually on my junior year math proficiency exam. We had to analyze that function, x to the x. Right. So if you want to stay up at night or something, just have that roaming around in your head. When is that defined? When is that? What is that guy's domain? And anyway, don't think about that. That might be better. So. All right. So what you are needing to do right now is to understand the shape, and you should already know what's going to happen to you. So you know the basic shape. The basic shape of an exponential is this. And then it could be reflected, it could be shifted up and down. So that's exactly what's going to happen. So what do? Once you know the shape, you only need like 3 anchor points. And these are the ones I would move around and shift and reflect. So my anchor points are always -1, 0, 1. So if I had to do the graph of, let's see, are you working better? Maybe. I had to do the graph of, you could do it, Jeff. There you go, buddy. Something. Okay. What are the shifts happening here? Uh-oh. Do you guys remember? What's the shift?
To the right.
Right, 2, and?
Down
1.
1.
No.
Oh. Up 1.
Up 1. If it's with the letter, it does the opposite of what it looks like. And we've talked quite a bit about why that is. And I know that can be very confusing. But if I put this with the y, it would be y minus 1. And then I would do the opposite of what it looks like. It's just the fact that it's not with the letter. That's why you do exactly what it says. You take that and you raise it up 1. So if I graph 3 to the x, my anchor points are 0, 1, 1, 3, -1, 1/3. Those are my anchor points. In fact, any a, the 3 anchor points, if this is a, would be 0, 1, 1a, -1, 1/a. Those are my 3 anchor points. So I know this looks like this. It's got an asymptote here, right? So now I take my points. Let me see. Are you going to work? Sure. Okay. So I take this point and I'm going to move it, like we said, right 2, 1, 2, and then up 1. So can somebody tell me where my asymptote is going to be?
At 1.
Yes, good. It's going to go up 1. The left and right doesn't matter because it's an infinite line. It doesn't give a shit about left and right. But the up 1, that's where it's going to go. So now it's here. Damn it. Sound like this one. Then I take this point and I go, where to go? Right 2, up 1. And then I take this point, right 2, up 1. And now I connect the dots and I'm done. So that should feel very familiar to the shifting that we did before, unless you're one of the special people that didn't actually do the shifting. You just copied out your calculator and you're going to have a rough time. All right. My special people. So draw the base function and then shift the points. Make sure you move the asymptote. It'll correspond to the up and down movement. I like it.
And if that was -3x to the negative.
So I think you can. Oh, I see what you mean. So that would be adding another shift on, wouldn't it?
Yes.
Yeah. So what would that shift be that you just added on? So if instead I had this. So what are my 3 shifts in the correct order? What's the one I have to do last? What's the shift I do last?
The reflection or the.
You actually follow order operations. So it would always be the vertical movement, right? So how do you tell shift order? It's the same as, well, the most important thing is what you would do last in order operations is the last shift you should make. So I got to do this shift last. So it'd be up 1 is the last thing I do. And then these two are whatever order. So I can go right 2. And then what's this going to do? Around which axis? So the Y's are becoming the negative of what they used to be. So if I make all the outputs the negative, which axis does it flip over? If I take a graph and I make all the Y's the opposite of what they used to be, isn't that just going to be a shift around the x-axis? A reflection?
Yeah, sure. Yeah.
I like that. Sure. Reflect x-axis. So I would have moved it right 2 and then reflected it. All right, so this gets more complicated, but so where would the, all right, let's do this. All right, this is going to be exciting. So you have green. Can you guys see green? Sure. So here's my base graph. So it'll be -1 1/3, 0 1 1 3. So here's my base graph. Then I want to make it right 2. So this is why I love my students who use like colored pencils. You don't have to. So right 2. So this would go right 2, right 2, right 2. So now I'm here. Then I'm going to reflect it. So that's going to now go, you should probably add in some lines here, Jeff. So now that's going to go here. That's going to go here. That's going to go here. So now they're all reflected around the x-axis. So now I'm here. The asymptote hasn't moved yet, right? Now I move it up 1. So every point I move up 1. Up 1, up 1. This is going to be a little freaky. This is going to move up 1. And where does the axis go to? There's too much going on here. I agree. But where does the axis go to?
1.
Move that too far? Let me see. My scale is really horrible here, but we'll survive somehow. So yeah, the axis goes up, up 1. So now it's going to be here. So now it's doing this. My scale is horrible, but oh well. So it's this graph just shifted up 1.
Okay.
So
thank
most
you.
important. Sorry.
I said thank you. Yeah, because I was getting confused as to when it would do the up 1.
Oh yeah. So it's sort of based on order operations, but not really, because the most important thing is to do this shift last. I've got to know what that is first before I can do this to it. So if that was -1, then I would do down 1 last, right? Whatever that is, I do it last. This is all one chunk, and I could do it actually at whatever order I want to. How do you reflect that? Is that cool? Did you see how? So I reflected it right after. So I wrote right 2. Then I reflected that. This is the reflection. And then I just picked the reflection up 1. And I did it in a really bad way because my scale sucked, but oh well. That's why it's good to invest in graph paper, right? Okay, I like it. What time we got? How do you guys feel? I think it's enough for tonight. What do you guys think? Is that enough for tonight? You guys want more? You want to analyze 0 to the 0? No, it's not doing it. All right, guys, that's plenty. Let me know if you need to hang out. Otherwise, you're free to go, and I'll see y'all tomorrow.
Thanks, Prof.
You're welcome, dude.
I have a question for the practice exercises you posted, chapter 5.3 to 5.6.
Yeah. Let me pull that up real quick.
Number 6.
Let's see, which one? Oh, I never put the answers up, did I? All right, the answers are, oh yeah, I was gonna remake this video. This is such a bad video, but oh well, too bad. There, all right. Let me see. Sorry. Where'd it go? Where'd it go? Where'd it go? Here it is. Okay. So which one?
Number 6.
Okay.
So I think this B is find out. I think slant asymptotes.
Yes.
The one side of the graph passes the slant asymptotes, I guess, when I graph.
Yes.
So you can actually pass the asymptotes.
Definitely. And I'm pretty sure I said that, but horizontal and slant asymptotes, what are they all about? They're about letting X get really big. So when X is not big, they're not in effect. So they're not the same. The vertical asymptotes are a real wall. You just cannot go through it, right? Horizontal asymptotes, they only come into effect when X gets really big. They are end behavior. So when I do end behavior and you say it's got to go up on both sides, right? Like it's an X to the 6th highest degree. What can it do in the middle? Whatever the shit it wants to, right? It can go crazy in the middle as long as at the ends it does this. So same thing with horizontal or slant asymptotes. What can it do before X gets really big? What can it do in the middle? It can go across that thing all day long because it's not really there. So that's the weird thing about horizontal and slant asymptotes. They only come into effect when X gets big. So you can totally cross both of them. You could cross a horizontal asymptote. In fact, maybe this didn't happen, but normally, I don't really make a point of trying to do this, but normally we do a problem like real quick, deal with me real quick. All right, where would the horizontal asymptote be here?
I forgot about this.
Oh, so the top degree is less than the bottom. Does anyone know what the horizontal asymptote would be?
0.
0. But what's the, there's a horizontal asymptote right here, correct?
Yes.
But what's the X-intercept?
1.
Huh?
1.
1. Right there. Do I have a point that is on the asymptote? Yes. So what would this thing do? This thing could do, I'm not going to do the whole thing, but this thing could do something like this. Where it goes through and then it says, oh shit, I better get closer to the asymptote now because now my X's are getting bigger. But when X is not big, it can do whatever it wants to in here. There's actually no vertical asymptotes, so it's kind of neat. I kind of want to do that problem, but oh well. Not right now. Maybe we'll do it next time. That's a real quick example of a very simple way to see that you can totally cross your horizontal or slant asymptote because I could have an X-intercept, but I could have Y = 0 as a horizontal asymptote. That can happen. Okay.
In that situation, the vertical asymptotes are the imaginary numbers.
Yeah, so they would only show up if we were graphing over the complex region, which would be neat.
Mm-hmm.
Because there's multiple layers of it. And so what we normally do when we graph complex numbers, and you've seen these images, we use colors, and the darker the color, the more imaginary it is. So it sort of tells us the level it's on. So it's sort of like anyway, I don't know if you guys are with me, but it's sort of like topological stuff where the color actually tells me if it's higher or lower. So if it's a really light color, then that means it's more real. And if it's really dark color, if it's black, it's like completely imaginary. That's one way to do it. That's not the only way to graph complex functions. But if you ever see a fractal and you see a lot of colors involved, different regions have different colors, then that could be a complex valued function being graphed. But let's not talk about that too much. Yeah, so in this case, there just is no real vertical asymptotes. So there would be no walls. So whatever we graph real quick is one slice of an infinite up and down selection. It's just one slice right in the middle. It's one slice, but then there's an infinite amount above it that's complex, and there's an infinite amount below it that's complex. And it's actually worse than that, but let's just not try to do that. Because I haven't even talked about there's another dimension within that. Because you got another axis that has to have its own complex parts. So let's not go there. Okay. Is that good? I went too far there. I know I did, but did I answer with the actual questions?
Yeah.
So I got a question like away from the topic you're talking about right now.
All right.
Do you do like retakes for any quizzes?
In certain situations?
Well, like I guess, yeah.
Huh?
Wait, give me 1 second. I'm just using my other mic.
I don't understand. What's up? Are you there? What happened? Hello?
Hello, can you hear me?
Yes. Now I can.
Like in certain situations.
Well, it depends on what happened to cause a retake to be necessary.
Well, I guess just like a low score.
Oh, if it's a low score, then you can make corrections.
Is there a lot of points I can get back with correction?
Now, all right, so I'm trying not to be a real dick here, but I was about to say, if only I'd told you exactly.
Yeah, I know. I've seen it on the syllabus, like 6
Yeah.
points, but like, is it just like 6 to like 10 points?
No, dude. If you got a 20, for example.
Okay.
And let me see, where is it at? Here it is. Yeah, and to be honest, I actually made it better than this. Yeah, I need to update this syllabus. So you could actually get more points back than what I say here, to be honest. But if you got like a 20, you could actually get 20 more points back, for example, right? That's still a 40, isn't it? But it's still 20 points more than you had before, and it might be exactly the 20 that you need to pass at the end of the class. So it's, yeah, depending on what your grade. Yeah, if you didn't make 100, I would make corrections. If I made a 99, I would make corrections. Right?
Okay. And then I got one other question.
Yeah.
So if I've been turning in a lot of like assignments, like the homework, and then it just keeps saying like either incomplete or show more work.
Sure.
So like, well, I don't really understand the part where you say show more work, because I'm showing like a lot of work, but like, can you like walk me through like what you mean when you say show more work?
We would have to look at one of your problem, but normally if I say show more work, I have indicated places where I needed to see more work.
Okay.
Yeah. So we might have a different definition of what work is.
Okay.
Yeah. So it depends. You might want to come to office hours and we can kind of go over. Sure. I'll see you. We can kind of go over your stuff specifically.
Okay.
Yeah.
Okay. All right. Thank you.
I actually had a question about the quiz also.
Yes.
I'm going to be out of town on the 11th from all weekend. I'm flying out of town. So